Welcome back to the next video, everybody. Today's video is going to be on character group schemes. So first of all, we're going to review the concept of base change just briefly from algebraic geometry, and we're going to apply it to our specific situation where we're talking about group schemes. Okay, so let's suppose U is an S scheme. So you're thinking you have a map from U to S. Okay. If T is also an S scheme, so you're thinking now about adding a bottom arrow to this diagram. Okay, then if we denote by U sub T the fiber product up here, U cross S over T, okay, then U sub T is called the base change from S to T of U. I like to think of the base change of U as a way to think of U as a T scheme. Now, of course, every T scheme V is an S scheme because T is an S scheme. Okay, and so you can also check pretty easily that U sub T of V is U sub S of V. And so if G is an S group scheme, the functor that sends V to G sub T of V is a group functor on this category of schemes over T. And so the upshot is G sub T is actually a T group scheme. Okay, so again, if G is an S group scheme, then G sub T is a T group scheme. You probably expected this to happen, right? Okay, every scheme S is, of course, by categorical equivalence, a Z scheme because every ring is a Z algebra. Okay, and our examples of group schemes that we've gone over in the previous videos so far, they'll have all been base changes from Z to R of Z group schemes. And this is really why, like the groups, G sub A of B, G sub M of B, etc., they only depend on B as a ring, that is, as a Z algebra, because of this comment here. They don't depend on B, thought of as an R algebra. Okay, and so from now on, we're going to write just G sub A, G sub M, GL sub N, D of X, etc., to refer to their standard versions over Z. And if I want to refer to their versions over S, their base changes to S, I'll write something like G sub A sub S. Okay, now, let's talk a little bit about global sections. So if T is an S scheme, we'll denote by B sub T the ring of global sections for the structure sheaf of T, which is denoted by O sub T, so that you can think of these as kind of the global functions on T, essentially, if you've never taken algebraic geometry. Okay. And so then by the above, again, because, of this comment here, the fact that these G sub A of B, G sub M B, etc., is only depend on B as a ring and not on it as an R algebra. We have, for example, that the T-valued points of G sub A sub S are just the T-valued points of G sub A. And then, of course, both of those are B sub T. You can see that by looking at the affine case, right? If T is affine, like let's say T equals spec A or something, then G sub A of spec A is the additive group A, but A is the ring of global functions on spec A, you see. So this whole discussion will follow essentially by looking at the affine case. Okay, similarly, we have G sub M sub S of T. That's just G sub M of T, right? And of course, that's just the invertible elements in B sub T. Okay, and then we have GL sub N sub S of T is just GL sub N of T. And really, that's just GL sub N of B sub T. And that's just, the invertible elements in M sub N of B sub T, where M sub N represents all matrices, N by N matrices here with coefficients in B sub T. Okay, and then finally we have, for example, D of X sub S of T is just D of X of T for the same reasons. And that's just the, homomorphisms of abelian groups from X to B cross sub T. And by this discussion up here, that's just the set of all homomorphisms of abelian groups from X to G sub M of T. Okay, and so we can get a handle on, essentially what I'm saying here is, we can get a handle on T points of base changes just by looking at the ring of global sections. That's really what's happening here. Okay, characters and group-like elements. So let's let G be an S group scheme. What's a character of a group scheme? A character of G is a homomorphism of S schemes, chi from G to G sub M sub S. Okay, or equivalently, if you like, it's a non-vanishing section or element of O sub G, the structure sheaf on G, such that M star chi is just PR sub 1 star chi, PR star sub 2 chi, where PR sub 1 and PR sub 2 are the projection maps, and this is happening on G cross G over S. Okay, of course, as you probably expected, the characters of G form a subgroup, which we'll call, Hom sub Gur over S, from G to G sub M sub S. That's a subgroup of the full set of morphisms in the category of schemes over S from G to G sub M sub S. And of course, this guy here is just G sub M of G by definition, right? But none of this is unexpected if you just think about characters from number theory, for example. If S is spec R and G is spec A, so if we have affine schemes, Then another way of thinking about a character chi of G is it's just an invertible element of A, such that m tilde chi, remember m tilde is co-multiplication, is just chi tensor 1 times 1 tensor chi, which is just chi tensor chi. Okay, so this is just kind of the ring theoretic version of the discussion we had above when we're working with affine schemes. If A is a Hopf algebra, we're going to call such a chi group-like, a group-like element of A. And the group-like elements of A, big shocker, form a subgroup of A cross, which we can think of as the group of characters on spec A defined over R. Okay, so a lot of this is just scheme theoretic versions of things you've already learned in other fields, in other classes like number theory and abstract algebra and stuff. Okay, so a very important topic here is the character group scheme concept. The functor that sends T to the GR over T maps from G sub T to G M sub T. So this is these are our maps from the base change of T to the base change of G sub M, the base change to T. Okay. This is a contravariant functor from schemes over S to abelian groups. If this functor is representable, meaning it's isomorphic to the functor of points of some scheme, the representing commutative S group scheme is going to be called the character group scheme of G, for good reason, right? It represents the character functor, right? So if G prime is the character group scheme of G, let's say that exists, then for each T in schemes over S, there's a pairing from G prime of T cross G of T to GM of T. And that pairing is given by, how do I give you a pairing? I give you a map from here to homomorphisms from here to here, okay? So here's the pairing. It's just a map from G prime of T, which is the GR over T maps from G sub T, the base change, to G sub M sub T, okay, to just kind of the group homomorphisms from G of T to G of M of T, okay? And this pairing is compatible with base change from T prime to T. And so what I mean by that is the morphism T prime to T gives the obvious contravariant commuting diagram of pairing. So draw out this pairing, acknowledge there's a map from T prime to T, make the obvious diagrams. Those are the diagrams that we want to commute. Okay. And so I'll just say a little bit more about character group schemes. You might wonder, like, all right, if I'm given a collection of these pairings that are compatible with base change, do I get kind of a character group scheme out of that? And the answer is more or less yes. If I give you two S group schemes, G and G prime, with a collection of pairings as above compatible with base change, this determines a homomorphism, G prime of T, into the group of homomorphisms of the functor G sub T, into the functor G sub M sub T. So draw all that out, what I just said, carefully, okay? Another way of saying that is we get a homomorphism of G prime of T into GR over T maps from G sub T to G sub M sub T for each T, okay? If these homomorphisms are isomorphisms, then the pairings that I gave you to produce this homomorphism, do in fact identify G prime with the character group scheme of G, as expected. And so in other words, under the obvious reasonable circumstances, the converse to this slide here holds. All right, so next time we're going to be looking at constant group schemes. And so I'll see you then, and thanks for watching.